Good morning everyone. Myself Karthik and I am very happy to get back to you. Today's topic is units, dimensions, errors and significant figures. Today we are going to discuss the theory of these topics in this particular lecture. Why do we require units and dimensions? Why do we require measurements in physics? So we all will say a very simple answer that units or measurements is very important in this subject because it is an application oriented subject. Yes, you're right. To apply, you need to measure. So to measure, you need to learn how to calculate. So I would explain this in my perspective. I always believed that we have developed this part of physics called units only because we wanted to make communication very easy. Again, we will discuss it with an example. Assume that it is winter where I live and I wanted to buy some pashmina shawls from Kashmir. And you all are very much aware that those shawls are very popular. So when I wanted to go buy the shawls and I want to sell it here so that I would make some profit. So I called from here, or I wrote a letter from here to Kashmir saying that please send me 100 meters of cloth. The length has to be 100 meters and the depth and the width is around 2 meters. So that I thought I will make some 100 shawls out of them and I will sell it here. So with a different price or at a different cost so that I will make some profit. Then I called them. They have sent 100 meters. So I received and I opened the package and I was shocked. According to me, I have a 1 meter long scale and I thought I would get 100 times that 1 meter which I have. Then I again called them and I asked, when I asked you 100 meter, you sent me very small amount of cloth, you did not send me the enough amount. Then they said, no, I sent you 100 meter. And then they took a photograph of their 1 meter rod and they sent you, or they sent that 1 meter rod through post which is very small. Here, according to them, the length of the shawl that they have sent, the cloth that they have sent is 100 meter. According to you, it is not. The reason is, you both do not have an agreement about what 1 meter is. So whenever you want to communicate, see for example, I will tell you another example. Suppose there is a person X suffering from fever. You wanted to tell that his body is hot or a phone to someone else. So you will touch and you will tell it is a feel. By feeling his skin, you will be telling, yeah, it is hot. Now immediately they will ask, how much hot? Or how hot his body is. Then you will say, not very hot, it is little hot. Or if it is too hot, you will say, it is very, very hot. So you have to measure, or the others have to understand the temperature of this particular guy's body based on the number of adverbs that we use. Very, 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 very hot. That means they have to assume that it is too hot. Because you do not have a way to measure. So, units are required as standards of measurements. When I talked about length, I spoke about meter. When I talked about temperature, I have to talk about degree centigrade. So, we have these units that are set up. And at the same time, to avoid practical difficulties, to avoid miscommunications, we should have an understanding about what 1 meter is, what 1 degree centigrade is. Only if we have that perfect agreement, we will be able to communicate very easily. So, the entire system will run smooth only if you have that agreement. So, that is why a unit is defined as a standard of measurement, which is accepted universally. Means everybody should come into an agreement of what it is. And once it is agreed, it should not be tough for you to make or reproduce the unit that you have designed and agreed upon. So I know 1 meter rod's length. What I can do, if I want another 1 meter rod, I will take a small tape or I will take a small rope, I will measure 1 meter and I will go to another carpenter and then ask him, please cut and give me a small piece with this particular length. So I reproduced another 1 meter length. So I can multiply the units. It is easy. The unit that you design should not be very complicated. It has to be easy. That is why a unit which is a standard of measurement and it is universally accepted, along with another point called it should be reproduced easily. And there is still more to it. Now, assume that I am from Rajasthan. We all are aware that in most parts of Rajasthan, days are very hot and the nights are very cold because of the arid conditions that are in and around Rajasthan. So, I wanted to again go to Kashmir, buy some shawls and come here, and I wanted to sell in Rajasthan. So, I went, this time I took my 1 meter metal scale and I went to Kashmir. I asked him, please give me 100 meter, please use this particular steel rod or 1 meter rod, please measure it. So they have measured in front of you and they gave you a like package and you brought them here, and before selling you wanted to remeasure that. When you measure it is coming only 90 meter. So you thought that guy cheated you when he was measuring. So what you did, you wanted to teach him a lesson. So you took this the cloth and the rod along with you and you went back to Kashmir and asked him, please measure in front of me now very slowly so that I want to check whether you have given me agreed amount of cloth or not. And so he said, yes, I will be very happy. So he started measuring it in front of you, but it turned out to be 100 meter. So you were not believing. So you started remeasuring it and you got 100 meter as well. Okay, so you thought, okay, I might have made a mistake back in Rajasthan when I was measuring. So you have decided, okay, you came back and you wanted to start selling. Before selling, again you are measuring, again the length is only 90 meter. It is the same unit, it is the same measuring instrument, and it is the same person who measured in two different locations. But what happens? When you go to Kashmir, owing to the low temperatures in Kashmir, the size of the 1 meter metal rod will decrease because metals contract on cooling. So you are measuring with a small cloth, and when you come back to Jaipur and you start measuring at hot temperatures, the length of the rod will increase and you are measuring with a longer scale. Naturally, the magnitude of the reading will be reduced in Rajasthan. So there is an added factor to a unit. A unit should never get affected by physical conditions like temperature, pressure and all. So now we have learned the necessity and the definition of a unit. The necessity of unit is not only because we are dealing with an application oriented subject. Not just that. Units are mainly first discussed and then decided all over the world because they are standards of measurement which are universally accepted. They are universally accepted. At the same time, they should be easily reproducible and they should not get affected by physical conditions like temperature, pressure, etc. That is the importance of units. So in this chapter of units and dimensions, we are going to see the following subtopics. Please make a note of subtopics that we are going to see. First one, introduction to measurements. We have already discussed a part of it by now. Second one, definition and necessity of units. Third, system of units and multipliers. Fourth one, dimensions and dimensional formula. Fifth one, applications of units and dimensions. Then sixth one, errors and error analysis. Then seventh one, significant figures while the eighth one would be measuring instruments. So in our discussion of theory in this chapter, units, dimensions, errors and significant figures, these are the subtopics that we are going to concentrate in this part of the video, and in the upcoming videos we will also deal with solving numericals in these areas at different levels. See, as I told you, the necessity of units is for better communication and to better measurement. I will also tell you another example. See, assume that we have a robot, a small robot which is doing small works for us at home. A robot is a machine with which you can talk, you can communicate in terms of programs. So here, when you are talking with it, you said, there is a beautiful table, a 1 meter long table. There is a beautiful glass flower vase at one end, and you said, my dear robot, please take that flower vase and move it to your right and place it on the other end. Please move it to your right by 1 meter. You have to be very specific in telling the calculations or measurements to any machine. So likewise you said, from your left, from the left end of the table, please take this beautiful glass flower vase and shift it to the rightmost end by moving it by 1 meter. So this is the size of your table, and when the flower vase is moved from one end to the other end, what this robot has done is, it came to the other end, it crossed and it dropped the flower vase here. So it is dropping it beyond, and it said, yes, I have moved it by 1 meter. Why aren't you happy? Then you said, you did not move it by 1 meter, you moved it more than 1 meter. Here again the problem is, even though it has done more work for you, it is not useful because you did not get the exact required output. You wanted it to move by 1 meter, it moved more than 1 meter because you both are not in perfect agreement with what 1 meter is. That is what I have been telling yesterday in the example, like in the earlier discussion I was telling about the need for agreeing on what a unit is going to be. So here with a robot or with the wool sellers in Kashmir or wool sellers in Rajasthan, everywhere you all should be in perfect agreement with what 1 meter is going to be. So that is very important, and that is why it is defined. We have already seen the definition of unit. Unit is a standard of measurement which is universally acceptable and easily reproducible, and it should not be affected by physical conditions like temperature, pressure, etc. Okay. Now, system of units. Why do we have different systems of units? See, today it is very easy to communicate from one country to the another country. There were so many developed countries before 60 years, 100 years, 150 years. They were all flourishing nations were there, and everyone, they were a closed country. Everyone was a closed country. So at that time, it is not easy to communicate on 1 meter everywhere. What 1 meter is in India, what 1 meter is in France, it is not easy to communicate. So there are some countries which developed their own system. See, for example, you have French system or European system, famously called FPS, foot, pound and second, and which they are still using. Even though while communicating with the other countries they use meter, kilogram and second, today they are still using foot, pound and second for them. That is why in some of the books you might have seen LB or the reading of mass given in terms of pounds. So different systems of units were generated earlier because the communication was not there and they were developing in their own closed manner. But today we are the entire world has agreed upon SI unit system international standard of units. They have agreed upon that, and today we are all using them. Now, different systems of units. First one, MKS system or SI system. MKS system uses meter, kilogram and second. Likewise, CGS system, it uses centimeter, gram and second. Then you have FPS system, foot, pound and second. So these are the different systems with multiple conversions between them. Now coming to multipliers. First we will see the positive multipliers and then the negative multipliers, where if you are measuring very large quantities or very small quantities, it is very easy to write the magnitude of any measurement with the help of these multipliers. Deca 10 power 1, hexa 10 power 2, kilo 10 power 3, mega 10 power 6, giga 10 power 9, tera 10 power 12, peta 10 power 15 and exa 10 power 18. Likewise, you have the 10 power minus multipliers as well. So it is deci 10 power minus 1, centi 10 power minus 2, milli 10 power minus 3, micro 10 power minus 6, nano 10 power minus 9, and then pico 10 power minus 12, femto 10 power minus 15 and atto, atto 10 power minus 18. These are the multipliers. And yes, suppose if they say 1 femtometer, what is its meaning? It will be 10 power minus 15 meter. Like that we will use them as replacements to this 10 power exponents of tens. So 10 power plus and 10 power minus, these are the thing. This is just memory based. You have to practice them and memorize them. Next, physical quantities. In our introduction, we have been talking about the feeling of temperature and a measurable quantity called temperature. So there are two different things. One is a feel. The way you touch and tell something, it's a feel. It is not a measurement. So physical quantities, these are the quantities which can be measurable. Okay. So anything measurable, they are measurable. So when you are measuring, they have to be expressed in terms of some standards called units. So there are two types of physical quantities. One is fundamental quantity and derived quantities. Fundamental quantities and derived quantities. The units of these fundamental quantities, they are called fundamental units. The units of these derived quantities are called derived units. Let us see what are they. We have totally 7 fundamental quantities and there are 2 supplementary quantities as well. They have some special property, that is why they are placed separately even though they look fundamental. But derived properties, we have n number of derived properties. We have large number of, other than these 7 plus 2, the rest all the physical quantities come under derived quantities. See, what are the fundamental quantities? First one is mass, then time, length, temperature, electric current, luminous intensity, and amount of substance. I am also writing their respective units next to them. Unit of mass, kilogram, time, second, length, meter, temperature, Kelvin, electric current, ampere, luminous intensity, candela, denoted by CD, amount of substance mole denoted by MOL. Other than these fundamental quantities, as I said, there are two supplementary quantities also. Let us see what are those two supplementary quantities. The two supplementary quantities are plane angle and solid angle. Okay. I will explain you in some time why these two quantities are placed separately. In a separate video, that is only to understand them, I will make a small separate video on this plane angle and solid angle and try to make you understand about them. Now, derived quantities. We have so many derived quantities. Like for example, you take velocity. What is velocity? Velocity is displacement by time, rate of change of linear displacement. So, the speed at which displacement changes. So, it is displacement divided by time. What is the unit of velocity then? Unit of velocity will be unit of displacement divided by unit of time. Unit of displacement is meter, unit of time is second. So, any physical quantity which depends on more than one fundamental quantity, that is called a derived quantity. The units of all the physical quantities which depend upon more than one fundamental quantities, those units are called derived units. See, we can write acceleration. If you take, it is change in velocity by time. So, what is the unit of acceleration? Unit of acceleration will be unit of velocity by unit of time. So, meter per second divided by second. So, it will be meter per second square. Likewise, force is mass into acceleration. Unit of mass into unit of acceleration. Kilogram into meter per second square. This kg meter per second square only, it is named after our famous scientist Newton. So, this is about different types of units. So, we are moving on to dimensions and the applications of dimensions. I would like to start with a derived quantity. Let us take force. We know just a simple formula of force is equal to mass into acceleration. If we are writing the units, unit of force is equal to unit of mass into unit of acceleration. Unit of mass is kg and the unit of acceleration is meter per second square. So, we get unit of force, the SI unit of force is equal to kg meter per second square or kg meter s power minus 2. So, I can write it as kg power 1, meter power 1 and time power minus 2. So, the unit of force is depending upon the unit of mass to the power of 1. The unit of force is depending upon the unit of length by 1. And the unit of force is depending upon unit of time as to the power of minus 2. So, here 1, 1 and minus 2. These are the powers respectively on which the force is depending on mass, length and time. So, these powers 1, 1, minus 2, these are called dimensions. To write them a little different, as we know, kg is representing mass and meter is representing length and second is representing time. So, the unit of force is kg meter per second square, whereas the dimensional formula, the relation is written as m power 1, L power 1 and t power minus 2. So, 1, 1 and minus 2 are the exponents to which the fundamental quantities m, L, t are raised to express a derived unit called force. Those 1, 1 and minus 2, these are called dimensions, and m power 1, L power 1, t power minus 2, it is called dimensional formula. So, how do we define a dimension? Dimensions are the powers. They are the powers or exponents to which the fundamental quantities are to be raised to express a derived quantity. Those powers or exponents are called dimensions, whereas the relation between them is called dimensional formula. This is the example. I will also tell you another example, pressure. What is pressure? pressure we know force acting per unit area of cross section. So P is equal to F by A. So that is pressure. Now unit of pressure is unit of force by unit of area. What is the unit of force? We have just derived kg meter per second square, and unit of area is meter square. So what do we get? It is kg per meter into second square, or kg per 1, m power minus 1 and s power minus 2. So in this same order, 1, minus 1 and minus 2 are the powers to which the unit of mass, length and time are to be respectively raised. So this 1, minus 1, minus 2, 1, minus 1 and minus 2, they are the dimensions of pressure. They are the dimensions of pressure, whereas m power 1, L power minus 1, T power minus 2, it is dimensional formula of pressure. So this is about dimensions and dimensional formula. Now we will move on to our next topic, applications of units and dimensions. Applications of units and dimensions. This is one area where a lot of numericals are to be solved, and we will also solve them in our subsequent videos. First one, principle of homogeneity. What is the meaning of the term homogeneity? See, this is principle of homogeneity. What is the meaning of homogeneity? Homogeneity means something looking alike. Okay, see, for example, we are adding two physical quantities. If I ask you what is the value of 2 meter plus 3 meter, your answer is going to be 5 meter. But if in the same place I ask you 2 meter plus 3 kg, is it possible for us to answer that? We cannot add 2 meter and 5 kg. It is not possible. Okay, so when we are adding two physical quantities, likewise when we are subtracting two physical quantities, those physical quantities should be representing, or those physical quantities should have same units. When you are adding two quantities, they should have same units, or they should represent the same physical quantity. That is the meaning. So I will be writing an equation here. If I say A plus B is equal to CD minus E by F. This is an equation. In the LHS we have A and B. We are adding two physical quantities A and B. In the RHS we are subtracting two physical quantities CD and E by F. So when we are adding these two physical quantities A and B, so A plus B, so the unit of A should be equal to the unit of B. Otherwise we cannot add them. Likewise here in the RHS we are subtracting CD and E by F. So the unit of CD should be equal to the unit of E by F. Now you take that single term CD. We are multiplying two physical quantities C and D. Multiplication does not have any restriction. You can multiply mass with velocity. You can multiply length with time. There is no restriction in multiplication or division. But here, since you are subtracting CD and E by F, those two should represent same physical quantities, or they both should have same units. If I add 2 meter plus 3 meter, the answer is going to be, okay, if I add 2 meter and 3 meter, then in the RHS the answer is going to be 5 meter. That means on both sides of the equality symbol also we are getting the same unit. So 2 meter plus 3 meter will be equal to 5 meter. Likewise, in these four terms in a given expression A, B, CD and E by F, unit of A should be equal to unit of B, which should be equal to unit of CD and unit of E by F. So in a given expression with multiple terms, all the terms should have same units. This is called principle of homogeneity. The next application is related to exponents trigonometric ratios, exponents, trigonometric ratios and logarithmic ratios. So, if you talk about exponents, exponents are nothing but the powers. So, if I have 2 power 2, I can write the answer as 4. But if I am going to calculate 2 power 3 meter, 2 power 3 meter can be written as, see 3 meter is in the exponent, 3 meter can be written as 3 into 1 meter or 3 into meter. So, this can be written as 2 power 3 whole power meter, or we know a power m whole power n is equal to a power mn. Using the converse of it, we can write 2 power 3 meter is equal to 2 power 3 whole power m. So, this is nothing but 8 power m. How can we find 8 power meter? It is not possible because it is only a standard of measurement, it is not a numerical value. 8 power m is not possible. So, it is very clear that in exponents or powers, there shall be no units. There shall be no units. This is another important application of it. Now, coming to trigonometric ratios. Here, I would also like to make a simple and very important point. See, you know, tan pi by 6. Tan pi by 6, if you take, pi by 6 is nothing but pi by 6 radian. So, inside the trigonometric ratio, whatever angle you are substituting, it is in terms of radian, or if I write it as tan 30 degree, I am using another unit called degree, where these two are related as, we know that these two are related in such a way that 180 degree is equal to pi radian. So, coming to that, if I write tan pi by 6 radian, we can specify to a unit called radian. That is why the angle, the plane angle and the solid angle, they are placed under a separate section of quantities called supplementary quantities, and their units are called supplementary units. The reason is, these two physical quantities have only units, but they do not have a dimension. That is why they are placed under supplementary quantities. So, did you understand this? Supplementary quantities are the quantities which have units but no dimensions. That means inside the trigonometric ratios, the angles that you are substituting should not have any dimensions. So, the angles should not have dimensions. So, inside the trigonometric ratios, either you can use radian or you can use degree as a unit, but not any other physical quantity with units. We cannot have any other units there. That is why they are placed separately also. Now, the third one is logarithmic ratios. See, just to a few of you, we can write, if a power m is equal to b, m is called the exponent, a is called the base, b is called the value of a power m. So, what is the definition of logarithm? Log b to the base a is the exponent, which is nothing but m. This is the definition of logarithm. Okay. Now, that is only for your reference, but otherwise, in this logarithmic ratios, suppose I am going to find out log 2 meter. Log 2 meter. We know a property in logarithm which says that log AB is equal to log A plus log B. So, here log 2 into meter, if you are actually writing, you have to write it as log 2 plus log meter, which is not possible because log of meter is not possible. Meter is just a unit, it is not a numerical value. So, it is not possible to find out log 2 meter. So, inside the logarithmic ratios also there shall be no units. That is another important application. So, in the exponents, in trigonometric ratios and in logarithmic ratios, there should not be units or dimensions. That is very clear. Only in trigonometric ratios you can have radian and degree, but not any other physical quantity because they are special. Supplementary units, that's why they are placed specially. This is another application. Third one, conversion from one unit to another. Conversion from one unit means one system of unit to another. See, we know the unit of force very well. What is the unit of force? Unit of force is equal to kg meter per second square. This is named after Newton. This I have already told you. 1 kg meter per second square. This is in SI unit of system. But if we consider CGS unit, the CGS unit is nothing but gram centimeter per second square, and this is named as dyne, denoted by dn, is named as dyne. So, when we are converting from one system to another system, let us convert and see what will happen. 1 kg meter per second square is equal to 1 kilogram is nothing but 1 kilo 10 power 3 gram, and 1 meter is nothing but 10 power 2 centimeter divided by same second, so second square. So, you get 10 power 5 gram centimeter per second square, or it is clearly 1 Newton is equal to 10 power 5 dyne. This is what is the conversion we got. Now, if you look at this, the Newton is a bigger unit when compared to dyne. The Newton is a bigger unit when compared to dyne. So, if you look at these two, see the magnitude in front of the unit. In the LHS you have in SI unit, so it is 1. In the RHS you have in terms of dyne, and you have 10 power 5. The bigger the unit, the smaller is the magnitude in front of it. So, the numerical value is inversely proportional to the unit. That is what we were able to write. If unit is bigger, numerical value will be smaller. So, n is inversely proportional to u, or n into u is a constant. So, we can write n1 u1 is equal to n2 u2. So, this is the principle we use in converting one system of units to another system of units. The bigger the unit, the smaller is the numerical value. Our next application is dimensional analysis. Dimensional analysis. I will solve it later in a separate video when we are doing numericals about using this dimensional analysis. Right now, I will tell you how we actually use this dimensional analysis. There is a physical quantity P, okay, and there are physical quantities X, Y and Z. Okay, before we go into this, there is one very well known fact that 90 to 95% of all the physical quantities available have their units in terms of m, l and t only. That is one thing that we have to understand. See, other four physical quantities, temperature, electric current, luminous intensity and mole, they come only in specific areas, but mass, length and time, these three physical quantities represent many derived quantities. So, 90 to 95% of the derived quantities can be expressed in terms of m, l and t only. So, considering these four physical quantities P, X, Y and Z, all four of them falling into our 95% category, we are trying to solve this. Okay. So, P is a physical quantity, X, Y, Z are three physical quantities, assuming that P depends upon this X, Y, Z. So, there is a relation between P with X, Y and Z separately. So, I can write P is proportional to X power A, because I don't know how X is affecting P. Likewise, I don't know Y is affecting P. Likewise, I don't know how Z is affecting P. So, I can write it as X power A, Y power B, Z power C, or P is equal to a constant K into X power A, Y power B and Z power C. where this k is dimensionless quantity. Dimensionless quantity. So this is k. Okay. Now the units of p or the dimensions of p are in terms of m, l and t. Dimensions of x, y, z are also in terms of the same m, l and t. So in LHS and RHS, when I equate the powers of length, means if I equate the powers of L, then I get one equation in terms of ABC. If I equate the powers of M in LHS and RHS, I get second equation. If I equate the powers of T in LHS and RHS, I will get third equation. So when I get three equations in terms of ABC, then I can solve the variables A, B and C. So if you are able to solve ABC, then you can establish a relation between P and XYZ. Just as an example, I will tell you. Suppose I get A is equal to 1, B is equal to minus 1 and Z is equal to 1 by 2. Then I can write P is equal to K into X power 1, Y power minus 1, Z power 1 by 2, like this. So by solving the three variables ABC, you can write a relation or you can establish a relation of P with X, Y and Z. So you can by this method establish a relation which is correct dimensionally. See, it may be or may not be correct according to laws of physics, but it is correct only with respect to dimensions. So I am going to give you a couple of statements here. The first one being, if an equation is correct dimensionally, is correct according to units and dimensions. So I am writing it as, if an equation is correct dimensionally, it may be or may not be correct as per the laws of physics, because you have used only this technique of using these dimensions. Second one, if an equation is wrong, dimensionally, it is not satisfying the dimensions, LHS dimensions are not equal to RHS dimensions, then it can never be correct according to laws of physics. It can never be correct as per physics. And third one, if an equation is correct according to laws of physics, if an equation is correct as per the laws of physics, then it should be correct dimensionally. It has to be, it must be correct dimensionally. So these three statements are very important. See, dimensionally correct equation may be or may not be correct according to the laws of physics. Dimensionally wrong equation can never be correct according to laws of physics. But an equation which is correct according to physics will definitely be correct dimensionally. So these are the three statements. So for an example, if we are writing x is equal to AB plus C divided by y. This is an expression. There are 5 physical quantities here, x, A, B, C and y. So if this equation has to be checked dimensionally, you have to write it like this. Unit or dimension of x is equal to the unit of AB plus C divided by y. So if an equation is correct dimensionally or not can be checked. So the correctness of equation, the first step in checking the correctness of a given equation is with the help of units and dimensions. Now coming to the next point here, When we found out the relation between P and XYZ, we wrote P is equal to K into X power A, Y power B and Z power C. So you wrote P in terms of ABC. And I said K is a dimensionless quantity. But do we have only dimensionless quantities in an equation? If you consider F is equal to G, for example, F is equal to G m1 m2 by r square. This is an equation. If you consider this, universal gravitational constant capital G is not dimensionless. But when you are drawing the comparison, when you are drawing the relation with the help of dimensions, you will not be able to find the values of dimensionless quantities. So numerical value of constants cannot be found. Numerical values of constants cannot be found. First thing, numerical values of constants can't be found using this method. The first one. And second one, assume that one of these 4 physical quantities is falling in the remaining 5%, which depends upon K, means temperature, electric current, luminous intensity and mole, amount of substance. We will not be able to solve for the 4th variable. So it is very clear that we will not be able to establish a relation if any one of the physical quantities is depending upon more than 3 fundamental quantities. So if any physical quantity is depending upon more than 3 quantities or more than 3 fundamental quantities, I am writing fundamental quantities, it may not be possible always. See, I am not saying it will not be, I am saying it may not be. It may not be possible always. It may not be possible always to establish a relation. And also, suppose assume that now P, X, Y and Z, all 4 physical quantities are falling in our 95%. So you have 3 variables, you are getting 3 equations from M, L and T separately. So and you are solving them and you are getting the relation. Now assume that P depends upon 4 physical quantities instead of 3. Then you will have 4 variables to solve, A, B, C, D. But you have only 3 equations with the help of MLT. So in that case also, it will be difficult to find out the relation. It will not be possible to establish a relation. So if a physical quantity depends on more than 3 derived quantities, then it may not be possible always. It may not be possible always to establish a relation. And if there are trigonometric ratios, if there are logarithmic ratios, we will not be able to find whether they are really there or not there. We can only represent everything with K. We cannot write the exact constants. Okay. Any trigonometric or logarithmic ratios involved cannot be found. Okay, cannot be found in this dimension analysis method. And fifth one, any relation that is established is only dimensionally correct, but may or may not be correct according to laws of physics. So you do not know the accuracy of the expression. So here the equation derived or the relation derived is only correct dimensionally. So these 5 points are limitations of units and dimensions, or limitations of using dimensions to establish relations, or limitations of dimensional analysis. See, so I am also writing the heading here in the beginning: limitations of dimensional analysis. Okay, so we end here with the part 1 of our this current chapter, units and dimensions. So what are the topics we have seen so far? We have seen what is a physical quantity and what is the necessity to study units, what are units, what are different systems of units, what are dimensions, what is a dimensional formula, how do we apply units and dimensions, at what stage the units and dimensions applications are going to end, or what are their limitations when we apply them to establish relations. So these are the topics that we have seen. In the next video, I would concentrate on measurements, errors, error analysis, how the arithmetic operations are affecting errors. Okay, and also measuring instruments like scale, our geometric box scale, and geometric box scale, vernier calipers and screw gauge. So my dear students, in the first part of units and dimensions, which I covered in this particular video, we have covered the following subtopics: introduction to units and measurements, definition and necessity of units, system of units and multipliers, dimensions and dimensional formula, applications of units and dimensions. We have covered these areas theoretically. In the part 2, I would be concentrating a lot on measurements. Measurements involve the measured value and the actual value, so obviously the calculation of error, and then how the arithmetic operations are affecting the errors. So that is called error analysis. Then significant figures, measuring instruments. Under measuring instruments, we are going to concentrate on, we will learn from our basic geometric scale, geometric box scale, and then vernier calipers and screw gauge. So these things we will deal in our second part of units and dimensions video, which will reach you shortly. Now, I would like to thank you all for encouraging with the introduction video, and thank you all for watching this part 1 of units and dimensions. Your support has given me a lot of encouragement. As I said, please see, share and subscribe. We have a long way to go and we are going very soon. Thank you so much.